So welcome to the first lesson on connected particles. Here we're going to be modelling mathematically the forces involved and the motion involved in particles that are in contact with each other somehow. To do that, we're going to be using Newton's third law. We'll talk about that in a moment. And in two scenarios. One, typically compression. We're going to look at something called the normal reaction force, where normal here doesn't mean the opposite of peculiar. It means 90 degrees, so normals and tangents. Here we're thinking about the normal reaction force. We'll explain that a bit more. And then also another situation would be tension. So here typically two things connected by a rope or a tow bar. And we'll look at pulleys and a few other things. First of all, though, this is the first lesson. Let's get started. So Newton's third law states that if object A exerts a force on object B, then object B exerts a force on object A with the same magnitude but opposite direction. You may have heard it said as every force has an equal and opposite reaction, or every action has an equal and opposite reaction. This is I think a clearer way of explaining it though. So here we'll take the hand as A and the wall as B. Okay, if A exerts a force on the wall, then this law is stating that the wall exerts a force on the hand that is equal in magnitude, so those arrows should be the same length, but opposite in direction. We actually discussed this before we broke up when I asked one of you guys to sit on a wheelie chair, and I said, right, push against the wall, and you are pushing that way, and yet you ended up moving this way. And so we use this as an explanation that despite pushing to the left, the fact that you move to the right must mean that there's another force involved. You might be pushing the wall to the left, but the wall is pushing you to the right, and that's what causes that motion of you on the wheelchair to move right. Another example might be two people on wheelchairs or two people on skateboards pushing against each other. If B pushes A to the left, A will experience that force to the left and move left, but B will also experience a force from A, and because B will move backwards. Even if only one person pushes, they don't have to both be pushing. If one person pushes, if B just on A, then they're both going to separate in that direction. It won't be that B stays still and A moves. Okay, they will both move away from where they started. And again, that's another demonstration of this equal but opposite force. And we're going to use that to model a few little problems. So here, basically, that very same problem, we've got two skaters, this time ice skaters rather than boarders. They push against each other and they start to move. The first skater, whose mass is 75 kilograms, moves with acceleration 3.7 meters per second squared, and the second skater's mass is 63 kilograms. Assuming that any frictional forces can be ignored, so pretending we're on ice and that ice is perfectly frictionless, what is the acceleration of the second skater? If you want, pause it, have a go, see what you can do. Here is my solution. So here we've got this situation where two people are pushing away from each other. And we're basically modeling, the only part of this we're modeling is the time between this position and this position where a force is being exerted on these two people. And so we're going to create just a simpler diagram. We've got A over here, of the first skater on the left, and then the second skater on the right. Okay. And so if they are pushing against each other, if the first skater is pushing on the second, then the second is going to experience this force from the first. We don't know what that is, so we'll just call it F newtons. But the first skater will feel the equal and opposite reaction. So equal F, but opposite in direction. Okay. And that's the only force that we need to include on our diagram. So here it says, assuming that any frictional forces can be ignored. So there's no other forces. We could, if we wanted to, think about the force of gravity pulling the person down through the ice, but we're just going to model the horizontal forces at this stage. We're not worrying about the vertical forces. Let's then consider what's going on with each. As with all of our modeling before, we can now basically revert to Newton's second law, F equals ma. That's the relationship, or that gives us a mathematical model for the relationship between forces and motion. So let's do just that. On the first skater, we're going to apply F equals ma, okay, just on this part of the diagram. There is only one force. So we'll just leave it as F, as we put it up there. The mass of that skater is 75. We told the acceleration is 3.7 meters per second squared. And so we get a value for the force as being 277.5 newtons. Okay. That's going to be useful. Let's move over to the second person. Again, do exactly the same thing. Once we've got our diagram, apply F. Now, I'm just going to take a moment to come back and label my positive. I should have done this at the beginning. My positive direction is going to be to the left. That's what I've done here. Positive force, positive acceleration as this object, as this person, first skater moves that way. Now, since the second skater is moving in that direction, okay, with some unknown velocity, sorry, acceleration, for A2, 1 equals, what was it, 3.7. We'll call it A2. This is now going to be negative because positive is towards the left. This is now towards the right. So that's going to be a negative acceleration. That's what we're expecting to come out at the end. But also the force. Here, the force was positive 277.5. Here, it's the same magnitude but opposite direction. So I'm going to label this as negative 277.5 equals the mass we know to be 63 kilograms. That's in there. And we're going to multiply that by acceleration. Okay. The fact that it's negative will come out in the answer. We don't need to put a negative in there. A itself will be negative if that's what it means. So here, we can then divide through by 63. So minus 277.5 over 63 kilograms gives us an acceleration of minus 4.4 something. So it's 404 something, who knows, but it's all round to minus 4.4 to two significant figures, and the units meters per second squared. And there's our answer. Okay. So all we're doing is applying those two forces in opposite directions. What I recommend is following this process of drawing diagrams, a separate diagram for each object, labeling all the forces involved. Second, apply F equals ma. Third, solve simultaneously until you end up with a solution that you're interested in. Have a go at this problem here. Okay, two bumper cars collide, the masses are, I'll let you read it. So pause the video and then I'll reveal my solution. Okay, here's my solution. So first of all, here's my little diagram. I've got two cars crashing. By the way, this is question 1 in your textbook. So I hope you've had a go And then what I'm going to do is I'm going to draw separate diagrams trying to label all the information for each one. So this is my diagram for car 1 and car 2. And now we're just going to apply F equals MA to each of them. Again, I'm just going to zoom out a bit. Okay, and so we end up with the following. That's not very helpful. Let's see if we can get it all in one. There we go. We're just going to apply F equals MA to the first. And we get a particular force, apply F equals MA to the second, substitute the force in from the first, and you should get your answer. That's basically as simple as it is. Have a go at the rest of the questions in exercise 19A. The solution to question 3 is under here, so pause the video before you have a go at the questions, and then if you're interested in the solution to question 3, there's my solution. Hopefully that helps you see how you can incorporate your constant acceleration formulas into that. Have fun.